LLM serving breaks during traffic spikes, unless batching, queues, and autoscaling are designed as one system. You'll learn how the pieces fit into a workflow that plans batches for surge traffic and stabilizes latency with queue controls. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Real systems fail when traffic jumps. One request at a time wastes GPU throughput. Too many concurrent requests and latency tails explode. Ray Serve Autoscaling for LLM endpoints fills that operational gap by treating batching, queue limits, and replica counts as one coordinated policy. Folks use this when they need a predictable P95 for chatbots without paying for a pile of idle GPUs. At small scale, you might see a baseline P95 of a few hundred milliseconds. At production scale, you want that tail to stay steady during bursts without keeping dozens of idle devices on. The intuition is straightforward. Group similar short requests so each replica does more useful work per inference call. Cap how many batches a replica will handle at once so the queue can't silently grow. Then, let autoscaling add replicas only when the configured capacity is truly needed. The payoff: better cost efficiency and smoother latency tails. The trade-off: batching adds headroom choices, and tuning requires measuring the right percentile. We will build a short sequence: a single replica baseline, then batching, then autoscaling aligned to batching, then tighter backpressure, and finally a quick regression to watch P95 during spikes. That keeps the code focused on the operational knobs you actually tune. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a minimal baseline to verify the endpoint responds before any scaling work. This snippet wires RayServe to run a single replica stub LLM endpoint baseline. It shows why a minimal deploy is necessary before tuning. Ray.init starts the local Ray runtime, and the @serve deployment decorator turns LLM endpoint into a serve deployment that simply echoes a prompt so behavior is obvious. Serve.run LLM endpoint.bind boots one replica and returns a handle you can call through handle.remote. Pulling the result with ray.get verifies the transport path end-to-end and confirms the deployment is reachable. The printed baseline reply is the simplest proof that later batching or autoscaling changes actually affect a working endpoint. Adding batching increases efficiency, but we must demonstrate coalescing works under short spikes. This example adds RayServe's dynamic batching, so the same endpoint can survive small prompt spikes. The delay S attributes simulates per prompt compute, while @serve.batch, max batch size 4, batch wait timeout second 0.005, tells serve to wait a few milliseconds to coalesce up to 4 prompts per replica. Inside call, we yield one response per prompt, so each caller still receives individualized output. Rerunning serve.run swaps in the batch deployment and the list comprehension issues 4 overlapping requests, letting serve form a single batch. If you increase batch wait timeout S, you trade higher latency for even fuller batches and better throughput. The printed response count confirms the batch processed every prompt and that batching did not drop calls. Now we need the autoscaler to understand batches, so it does not over or under provision. This code aligns autoscaling with the batching behavior by explicitly configuring RayServe's deployment limits. The dictionary in autoscale config keeps one warm replica, but allows serve to scale to 3. while aiming for 2 ongoing requests per replica, matching the 4-request batch ceiling. Serve.run redeploys the same LLM endpoint with those limits, and we immediately push a 6-request burst to ensure the new policy is exercised. Capturing target and capacity from the config quantifies how much headroom the autoscaler has before saturation. Watching those values and the printed capacity margin shows whether the burst fills the configured envelope or if the autoscaler added the expected replicas. Long bursts can still let a queue grow. We tighten the guardrails so queue length is bounded. This snippet tightens backpressure so the queue cannot quietly grow during longer bursts. Updating autoscale config reduces target ongoing requests and max replicas. Then LLM endpoint.options deploy hot reloads the deployment with a stricter max ongoing requests equals 2. That forces serve to keep only 2 in-flight batches per replica even while autoscaling is enabled. The burst list mirrors earlier load so you can compare timings apples to apples, and the timer around rain.get captures the wall clock duration of that constrained run. Lowering target ongoing requests further will smooth latency at the expense of throughput headroom. The printed burst latency reveals how much delay remains under the tighter guardrails and whether you need more replicas or a larger batch size. Finally, we run a tiny regression to watch tail latency as traffic patterns escalate. This example wraps the pieces into a quick regression so you can monitor whether the tuned RayServe endpoint still honors latency goals. Burst latency fires a burst of requests, uses the shared handle to issue them asynchronously, and returns the milliseconds consumed once all replies finish. The comprehension then runs 3 escalating bursts to mimic the kind of traffic patterns that usually trigger incidents. By sorting the collected latencies and picking the 95th percentile index, you can watch for tail drift without standing up a full observability pipeline. The printed P95 latency number confirms whether the tuned deployment holds its target during the sample spikes. Mapping this toy setup to production is straightforward. Use real chat logs as the request corpus. Keep the same burst shapes and plug actual model latencies into delay S. Swap the echo endpoint for your loader and inference call, then run the same P95 regression before you flip traffic. What you get is a repeatable way to coordinate batching, queue limits, and autoscaling so tail latency behaves predictably. Use this pattern when you need stable P95 for chat or assistant endpoints under bursty traffic. Remember, batching raises throughput but can increase median latency, and so needs active tuning for the tail. Next steps: sweep batch wait timeout S against your real chat logs while measuring P95 and throughput. Try values from 0.005 upward until you hit your latency SLA, and adjust target ongoing requests so autoscaling only adds replicas when real headroom is actually exhausted. If practical AI engineering helps you deploy reliable LLM services, subscribe and watch the AI engineering videos.